Okay, moving on to surface. Actually, I should move these a little bit over. So what happens when you try to do the same thing over a surface? So suppose I have a surface. Like that. I mean, it doesn't have to be a square. It could be any surface. May I define a small segment in that surface? Will that DL, that tiny DL, the width, carry a current through it? Griffiths defines that current per unit width as surface current density. And he calls it K, to be defined as DI over DL. And for the whole surface, he defines K as sigma V. Here we defined the current as lambda V in A. Here he's defining K as sigma V, where sigma, he calls it the surface charge density. And he says these are vectors. And going backwards now, we define force, that a current carrying wire makes a magnetic field as F equals IL cross B. In this case, we can define FB as K times B over area. Actually, I should have written here that in the integral form, FB is I integration DL cross B. Make sure to add the integral form. Now this picture, the last picture is going to be interesting to draw. I'm going to try it. Oh, I don't know if I'm going to succeed though. We'll see. Now, what if number 3, the flow of charge is over a 3D region? In this case, the flow of charge is over a 3D region. I'm going to try to draw this. Hang in there with me. So here in the 2D case, we defined it as surface current density. What do you think we'll define that as here?
volume current density?
Volume current density. So in this case, the volume current density will be the current per unit area. In this case, the current will be current per unit area that we chose as the volume current density, and we call it J. That's how they define it. And J is defined as DI over DA perpendicular. And for the volume, rho V, where rho is the volume charge density. And V is just the velocity, right? Which means how will I write the FB, the force?
Cos B. Oh.
Something like that? Woohoo! CJ, is that what you said?
Yeah, I didn't see that you're writing it. Yeah.
Oh, no, I heard you and then I wrote it and I was like, I was just wanting to make sure because that's what I heard you say. Because I usually write it with d tau, but dV is just perfectly good. Do you see the similarities between all of these equations? They seem really scary, right? When you first think about it, if you were seeing this in isolation, these are scary formulas, right? But once you start seeing how they flow from one to the other, you're like, yeah, I got this. They're not really different. It's just I'm just making these small changes in them, and that's what's making it different. So it's not really that different. Like, look at it. They're pretty much the same. All we did was we tweaked it slightly to go from one point to another. Wow, look at that table. Look how perfect that looks. Look at how pretty that looks. And that's like, I think that's like all of section 1 from Griffiths, which is all of the details and all of the math in there, just in one page.